Okay students, in the final portion of this lecture, we'll look at an application of all that we discussed to a theorem that we already introduced in the beginning of this portion, right? So remember we said that if you have a positive definite matrix, right, then every minor, right, so if you start with the positive definite matrix n cross n size, you can take any principal submatrix, right? So principal submatrix is obtained by taking, a certain number of certain rows of the matrix and the columns of the same indices as the rows, right? That will give you principal submatrix, right? Now if you take a leading principal submatrix, a leading principal submatrix is a submatrix that's formed by taking from the top left. So for example, this will be your 1 cross 1 principal submatrix. This will be a 2 cross 2 leading principal submatrix. This will be the 3 cross 3 leading principal submatrix. And let us say this is a 4 cross 4 matrix, n is 4. Then you have the 4 cross 4 leading principal submatrix. So when n is 4, you'll have 4 leading principal submatrices, right? This 1 cross 1 matrix, this 2 cross 2 matrix, 1 cross 1 matrix, this 2 cross 2 matrix, this 3 cross 3 matrix, and the overall 4 cross 1 matrix. These are the 4 leading principal submatrices, right? We said in the beginning that if A is positive definite, then each of these are positive definite, right? If A is positive definite, then each of these are positive definite, and we proved it also by constructing the quadratic forms. Okay. A consequence of that is that all these leading principal submatrices have positive determinant, correct? Because if each of them is positive definite, then determinant will be positive. Determinant is a product of eigenvalues, so determinant will be positive. Okay. I mentioned that the converse is also true. Okay, the converse saying that if all leading principal submatrices of a matrix A have positive determinant, then A is a positive definite matrix. Okay, if all the leading principal submatrices of A have the positive determinant, then A has a positive. A is positive definite. This is called the Sylvester's criterion for positive definite matrices. Sylvester's has popped up at least 2 or 3 times in this lecture, I think. The Sylvester's criterion for positive definite matrices. Okay. If in some context finding determinants is easy, let's say you have these matrices with some structure and you know that finding the determinant of each of these portions is very easy, then this gives you a very nice technique, a very simple technique to check if a matrix is positive definite, right? You can just start from the top left, keep building the principal submatrices and keep checking their determinants. If all of them happen to be positive, then the overall determinant is positive. Okay. This is called the Sylvester's criterion for positive definite matrices. Now, how do we prove this, right? When I mentioned this theorem before, I said that, we are going to differ the proof, right? And we'll prove it now, okay? The proof that we are going to do is going to be based on induction, right? Most of you are familiar with mathematical induction, right? So mathematical induction is the idea that, let's say you are trying to prove a statement that applies here to all, symmetric matrices, right? So we're starting with symmetric matrix and we are saying that if the determinant of all these leading principal submatrices is positive, then the matrix is positive, right? You're trying to prove a statement about matrices, then you start by proving it about the small size matrices and then you build on top of it, right? So you first prove it for a 1 cross 1 matrix, okay? That's the idea about induction. And then you assume that it is true for n cross n and use that to prove it for n plus 1 cross n plus 1. Okay, most of you know what it is. I'm just recollecting the main idea here, right? So if you prove, let's say, the Sylvester's criterion to be true for all n cross n matrices, for all n plus 1 cross n plus 1 matrices, provided they are true for n cross n matrices. Okay, this is called the induction step. Okay, in the induction step, we assume that it is true for n cross n. That somebody has given it to us that it is true for n cross n, and then we prove for n plus 1 cross n plus 1. Okay, and we also prove for 1 cross 1. Okay, so what is the main idea here is that if I prove for 1 cross 1, then by the induction step it must be true for 2 cross 2 as well. Okay? Then again applying the induction step, it must be true for 3 cross 3 as well. Then again applying the induction step, it must be true for 4 cross 4 as well, and so on and so forth. Then it proves it for all n cross 1. That's the main idea behind induction, very coarsely speaking. Okay? So that's what we'll try to do here. So let's try to apply, see if this is true for 1 cross 1 matrices first. Right? So if you have a 1 cross 1 matrix, that's just a scalar, so it just has one entry A. What does this Sylvester's criterion say? If the determinant of this 1 cross 1 matrix is positive, then the matrix has to be positive, definitely. Is that true or not? And if the determinant is positive, what is the determinant of a 1 cross 1 matrix? A. Okay. What are the eigenvalues of this 1 cross 1 matrix? What's an eigenvalue of this matrix? A is an eigenvalue. Is that clear to everybody? Again, I'll leave this as an exercise. If you have a 1 cross 1 1 cross 1 matrix, its eigenvalue is the entry of the matrix itself. I hope that is obvious to everybody. So let us say you have this. So the determinant is same as the eigenvalue here, right? So you're saying the determinant is positive, that automatically means the eigenvalue is positive, that automatically means the matrix is positive, definite. And I also mentioned to you before, right? For 1 cross 1 matrices, positive definite and positive is the same thing, right? Fine. So this statement is definitely true for 1 cross 1 matrices, because if the determinant is positive, then the 1 cross 1 entry itself is positive, which means the matrix is positive, definite. Let's assume it is true for n cross 1, n cross n, and try to prove it for n plus 1 cross n plus 1. Okay, assume it is true for n cross n, and try to prove it for n plus 1 cross n plus 1. Okay, so how do we do that? Right? So you have a matrix M, let's say, that is big, meaning it's n plus 1 cross n plus 1. Because I already know the result to be true for n cross n, a natural thing to do will be to partition, right? So I'm going to partition it like this. So let's assume that this is like M1. Okay, now this will be some 1 cross 1 scalar, so let's call it beta. Okay, and this will be a vector, let's call it alpha, and this will be alpha transpose, because it's a symmetric matrix, right? It will be alpha transpose. So alpha here is n cross 1, beta is 1 cross 1, and M1 is n cross n. Okay, fine. Now what is what I'm trying to prove, that the Sylvester's criterion is true, meaning that if I know that all the principal minors, right? So all the principal submatrices have a positive determinant. Okay. So let's say this is a 4 cross 4 matrix, then M1 will be 3 cross 3, right? So I know that all the principal submatrices have a positive determinant, then the overall matrix is positive determinant. So let me just write down very clearly what is given to us. All principal or all leading principal submatrices of M have positive determinant. That's given to, right? Okay, so what is the first conclusion that you will make? Okay, I'm immediately going to conclude that M1 is positive. Somebody tell me why that is. Again, keep forgetting that these are not live lectures. But if M1 is positive, how do we conclude that M1 is positive? Well, this actually means that the leading principal submatrices of M1 also have a positive determinant, right? And M1 is n cross n, so I assume the Sylvester's criterion holds for n cross n, right? That means by the Sylvester's criterion, M1 must be positive definite. Okay, this is basically what is called the induction hypothesis. It comes from the induction hypothesis. Okay, i.e., Sylvester's criterion is true for n cross n. Okay, that's where this is coming from. Okay, so M1 is positive. That's fantastic, right? Okay, in addition to the information that I already used here, what is left, right? The piece of information that I did not use it yet is that this overall matrix also has a positive determinant. Okay, I already used the fact that these matrices have a positive determinant to conclude this, right? I am left to use the final piece of information, so let me use that, right? So this overall matrix has positive determinant, that means det M is positive. But what is det M? I am going to write det M as det m1 multiplied with det of beta minus alpha transpose m inverse alpha. Okay, this is coming from this quantity over here is actually m by m1, the Schur complement of m1. Okay, we are using our result that the determinant of a block matrix is equal to the determinant of diagonal block multiplied with the Schur complement of that diagonal block. Okay, that's the result we are using here. This is the Schur complement, right? It's beta minus alpha transpose m1 inverse alpha. Okay, this is m1 inverse, m1 inverse alpha. Okay, now m1 inverse exists, right? Because m1 is positive definite, right? M1 inverse also exists. So Schur complement is well defined. Okay, fine. Now this is known to be positive, right? Okay, that's piece of information that's given to us, right? From the conclusion above, from the conclusion over here, you know that this is also positive. Okay, that m1 is also positive. That naturally implies that this is also positive. Correct? Now remember, this is just a scalar here, right? This is just 1 cross 1. Okay, beta minus alpha transpose m inverse alpha is 1 cross 1 because beta is 1 cross 1. So I might as well remove the determinant. You don't really need to say determinant, right? Because for a 1 cross 1 matrix, the matrix and the determinant are the same, right? So what that means is that this quantity is positive, right? So this implies that m by m1 is positive. Okay. Now here is where we are done. What we have proved here in the first statement is m1 is positive. This directly comes from the induction hypothesis. And what we have proved here is that the Schur complement of m1 is also positive, right? And the result that we discussed in the very beginning of this lecture and the one that we proved in the previous lecture is that if a matrix, block matrix is positive definite and the Schur complement is positive definite, that implies that M is also positive definite. Okay, matrix and a Schur complement are both positive definite, then M is positive. Okay, fantastic. So that's actually a proof of the Sylvester's criterion. I just included the proof so that it puts together all of these things. Schur complement arise very often in engineering applications, right? I sometimes say Schur complement, I sometimes say Schur's complement. I am not myself clear what to use. But anyway, Schur complement arises very often, especially when you work on probability and statistics. Okay. Remember, Schur complements will come whenever you are thinking of eliminating some set of variables, right? When you do probability later, you'll come across a scenario where, let's say you have a set of values, let's say x1, x2, xn, all of which are random, right? These are quantities that are all random. So it's a vector that's random essentially. You don't really know how to handle it. It's a vector that's random and you're trying to do some analysis on it. Maybe you're trying to estimate some of these values or something like that. But let us say you know some of these random values. So let's say x1 and x2 you have measured. So you know the value of x1 and x2, but the others you don't know. They're still random, right? So in some sense you are given some information, right? So you are given x1 and x2. Okay. So under these conditions, you will see Schur complements come up, right? So when you try to look at the statistics of the remaining set of variables and you try to find, for those of you who know, when you try to find their covariance matrix and things like that, that's when you start getting the Schur complements into play. Okay, so they have a wide variety of applications in estimation, probability, statistics, and I would say that, and even in optimization. Okay, most of you, I think some of you will do a course on optimization the next semester. You will see Schur complements come up a lot even in that context. I'll just leave it as an exercise. There is another proof of the Schur complement. It's slightly more complicated, but it's also not beyond our reach, right? It's using the interlacing theorem. Okay, in hindsight, I think I'll leave it for one of the exercise problems, one of the assignment problems. Okay.